Chapter 7, sorting. So in the previous chapters, like chapter 2, 3, 4, and 5, and we talked about a couple of different data structures. And when we talk about the operations on those structures, sometimes we assume that this structure is the data elements are sorted in this structure, like a sorted array or sorted list. Or sometimes we use max heap, and in the max heap, the data is not actually sorted, but in a sense, it's kind of sorted because the maximum element is always at the root node, okay? Something like that. Or binary search tree is kind of sorted too, okay? So basically, sorting is quite important operation here. So we have a separate chapter about sorting. So basically, we will learn a lot of sorting algorithms, and we will compare these sorting algorithms. Sorting has many applications as in the graph theory and optimization and job scheduling. Okay, so in this chapter, we'll focus on all these sorting algorithms, and especially we'll talk about some specific algorithms, okay? So insertion and quick and merge and heap and radix and external sorting algorithms. First of all, let's talk about the list. We already talked about list, right, in chapter 2, okay? So list is a collection of information in memory, and the file is a collection of information stored externally, like in a hard disk. And let's assume that our data is given as a matrix in this way, and then the row corresponds to one record, and the one column corresponds to one field, okay? And the key is a field to identify records, and when searching a list of records, we wish to examine the records based on the key field. Actually, we use this key in the binary search tree, okay? So I think you're already familiar with the key. Okay, so all the operations are based on this key, okay? So search is to find one record with a desired key value. Okay, we already did that in the binary search tree. Okay, and the sorting is to arrange the elements of a set into order. So basically, we have two different orders: ascending order and descending order. Okay. So in this slide, we have a structure to have a key and the other fields. I mean the data fields. Okay, so this is one structure. And basically, we're going to use an array of this structure. So element, list, max size. We learned linked list, and we learned trees, and we didn't talk about graph, but basically we can use graph and some other structures. But in this chapter, basically we're going to focus on an array. Okay. Now let's talk about a search. Okay, so in the search algorithm, if this array is not sorted, then what should we do? Basically, we have to check all the elements. So in this for loop, okay, so I goes from 0 to n-1, and checking if this element key is the same as search number. Search number is the target key. Okay, so if the list I.key is the same as search number, then we found it, then we can quit this for loop, and we return. If I is less than n, then we return I, because list I is the target element, okay? Otherwise, we return -1, which means we couldn't find the target number here, okay? Don't get confused. At the end of this for loop, we have a semicolon, so for loop will iterate until we meet some conditions. So we have a condition here: I is less than n, and list I.key is not the same as search number. So depending on this, the value of I, then we can be sure that we have the target in the array or not. So with these simple search functions, let's talk about the computational cost. Okay. So complexity of average case is n in a big O notations. Okay, so basically, if we are lucky, then just one iteration is enough. because the first one is our target number. But if we are not lucky, then we need n times comparison. Okay, so basically on average we need n plus 1 divided by 2 times comparison. Okay, that's our computational cost. So in a big notation it is n. But as you know, if we can assume that the list is ordered, then we can apply the binary search. Okay, I think you're already familiar with this implementation. So, with these functions, the computation cost is log n, right? So whenever we compare, we can narrow down our interest into the half of the list. On average, the log n is enough. And as I said, the number of comparison in the binary search is the height of decision tree, which is a log n in a big notations. So for example, given this list or array, then we can represent this list with a binary search tree. Then it looks like this. Then the height of this tree is the number of comparison. Okay. Here's an interesting question about the search. We are going to talk about the interpolation search here. So the question says, do we do sequential or binary search? Okay, so sequential search is really terrible. Okay, the computationally is not efficient. Okay, and the binary search is really good. Okay, log n is really great. But the question is, when we search in our daily life, when we search something, then how do we do? Do we use a binary search? Think about a dictionary. So we are looking up a word, then how do we do that? Yeah, suppose you are looking up a word William from a dictionary. Okay, then you start neither from the first nor the middle of the dictionary. So if we use a sequential search, then you start from the first page. Okay, and if you use a binary search, then you start from the middle page of the dictionary. But that's not how we do, right? So William is kind of around, we know that is around at the end of the dictionary. We already know, we already have some information about this word and information about the distribution of the words in the dictionary. So basically, we can start from somewhere like at the end of the dictionary, okay? So if our target word is something like student, then we basically roughly know where it is in the dictionary. Okay, so we can calculate the I rate in this way. So search number minus list, the first key. So search number minus first key divided by the last key minus first key. So the last key minus first key defines the range of these keys. And then search num minus list, the first key means distance between the first key and the search num, target number. So this ratio defines the relative locations of the target number. Okay, so the behavior of the search depends on the distribution of the keys in the list. That's how we do actually. So we know how these words are distributed, and we know some information about these words, the target word, and then roughly we can estimate the location of the word without looking at some specific things. So we can use some prior knowledge about this distribution and the target word. That's how we do this interpolation search. Okay, but in this chapter we are not going to talk about this kind of search. Okay, we don't have any idea about the elements, the arrays.